is a density matrix, the pure dead state. The other one is the signal to noise ratio. And if we measure that, we can figure out all these things.
That's interesting. I'm kind of, because before I was like not dealing with anything to do with relativity or anything. I was kind of leaving it aside and just focusing on group theory and quantum mechanics, and that was fun.
Yeah.
But I've kind of realized now, you know, like, I have to bite the bullet, and so it's interesting. Yeah. So hopefully I can work more with you guys on that kind of front.
So the interesting thing is, Emmanuel also said the same thing. You know, we were arguing against the relativity, but finally his PhD also, he said his people wanted him to do more relativity thing, you know, because that is established. So he doesn't have a choice. No, so he has to.
Also,
and I think you are also very similar.
Well, you know, I think it's spot on.
But I believe, and the surprising thing, I hope I'm not frozen.
Because you look at the James Webb Telescope, and you look at the results that came back, and those galaxies, and they're all warped and all. Yeah. Now, and obviously, you could have like that. It's not space that's warped; it's the light that's being warped. Yeah. You know, you could say that, couldn't you? I mean, that's valid, but okay. What about the other evidence that John gave the last day about there's some very big force at the center of the galaxy, and all of the stars are going around it. I looked into that, and
like water falling into this thing, right? Draining water.
Well,
water draining into things.
Yeah, it's an analogy for what's going on, and the stars are flying around it, and I was like, well, why is there no lensing there? And he said, well, it would have to line up perfectly with the black. And I was like, oh, okay, all right. So you know, that was my final sort of that got me thinking, you know, maybe there's something to this. And then there was a couple of other things, because you see, I've been looking into a lot of alternative theories to do with the Michelson-Morley experiment, and how the reason why there was a null result wasn't because was actually because the Earth was stationary. You know, this whole idea of the axis of evil, that they sent out all those space probes to look into at the CMB, and they found that it was aligned with the Earth's is it not the equator? It's the I think I've frozen again. You froze. Not the equator. The plane of the ecliptic. It is not frozen, but it is.
You got frozen 1 minute.
I know. Yes. So did you?
Frozen 1 minute.
I stopped talking. I waited until it unfroze, so that's good. I like when it freezes on both sides, not just one side. Yeah. That's then that gets annoying. But so So the whole. Can you imagine, like, we're this tiny little planet in space, and the entire cosmic wave background radiation is like aligned with our planet? It seems a bit unlikely. Oh, and also I did a whole back in March. I don't know if I told you about this, but I did a whole investigation of I'd have to look into it again. The distribution, the anisotropy of the universe, and I showed that it's not normally distributed. I have to look at it again. Sorry, my brain.
It's anisotropic. You are saying it's anisotropic?
Here it is. I can show it to you. Will I? Will I share this? Let me see. No, the word. I don't see it there. I don't know why it's not coming up. I don't think. Anyway, I'll just read it off. This research project seeks to impute the missing galactic data in the Sloan Digital Sky Survey using advanced data analysis and big data storage processing methods. It contains a critical evaluation of the. Okay, hang on. I'll just skip to the best bit. The research applies a structured. No, hang on a sec. Okay, yeah. The research applies a structured methodological application of linear regression neural networks and an in-painting convolutional neural network called Deep Image Prior to impute missing data in the Sloan Digital Sky Survey 3D map of the universe. In so doing, speculatively confirms the existence of the great attractor, possibly reveals the inhomogeneity of the universe, and discovers the local redshift and intensity of potentially millions of new galaxies. So that was what I did back in March. And it is pretty good. I want to do a bit better, but basically what it means, the inhomogeneity of the universe is that, you know, you have the isotropic, the universe is isotropic, yeah, but then you kind of see a slight anisotropy in the CMB radiation, but that it's certainly considered homogeneous, that it is the same in all directions, and it's like it would only be inhomogeneous if it turned out that there were like shells surrounding the Earth, you know, because like such a thing would be very centered on the Earth. So, but then they did find, looking with the you know, Sloan Digital Sky Survey, that there are these bands of galaxies, and there's like loads of galaxies in a circle, and then no galaxies, and then loads more galaxies in a circle. So, but they can't see all of the sky, you see. So they were like, oh, well, it's probably in those areas that we can't see. It's all just messy, you know. So I just used a machine because they've less bias, and I said, you know, you finish these images for us so that it eliminates the bias, and it basically, it not only did it fill them in, but it said there's a big load of stars in this portion here that we can't see. Oh. And indeed, like that's what we know is there based on all our models, because everything's being sucked in that way. So, and it consistently places a big chunk of stars there and very little. So I thought that was really cool. And again,
you have access to a radio telescope?
No, but I can send you on the links, because it's incredible.
How did you measure? I mean, somebody measured it for you?
Absolutely, yeah.
Where were they located?
Yeah, Sloan Digital Sky Survey has 2 telescopes. One is in probably not far away from you. I can look it up. And the other one is in South America.
Chile, maybe?
Oh, well, when I say I was going to look at it, I was just going to check the
There's a lot in Arizona. Arizona itself, I have gone only very few places.
Yeah, it sounds like it might be in Arizona, but I couldn't tell you without looking it up. It's began its legacy, represented the largest digital camera in the world, and was capable of taking up to 640 spectra simultaneously. I just want to see if it mentions anything about where it is situated. Each of the projects generates its own data. I would say there's this thing, right? The SDSS team has developed Sky Server, which is a cloud-based computing platform built upon the Microsoft SQL Server database. So basically, they have this really cool thing where you can query their database, and it'll give you, like, you know, loads and loads of data in terms of data sets and images. And it's just really, really, it's impressive what they have. And they even have tutorials, and it's all free. So you just sign up and just run the tutorials. You'll have a great time. I can send you a link to that if you want. Would you like that?
You will be studying more about that because you'll be in space physics, right? You're going to be PhD.
See, this is it. When I was doing this project, I was like absorbed in it, and then I was looking for PhDs at the same time, and I found the space data one. So it was all like, oh yeah, I'm doing stuff on space, and here's all my work, and I thought that they were looking out into space for anomalies, and so even like a good month or 2 into my application process, I was still talking about galaxies and all of this, and he was like, no, look up what we're doing. And I was like, okay.
Maybe, yeah.
I'm
getting, yeah, that's good.
Yeah, no, I had to look up what they were actually doing, because what they're using satellites in space, but to look at the Earth. So and for some reason that just wasn't apparent to me at all. Like it just didn't click until I looked into Swarm, the ESA Swarm satellites, and then I realized I was so confused for a while. I was like, why are they looking at the Earth's magnetic sphere, or you know, why aren't they looking out into space? And then I was like, oh, okay, this is a different. And that was funny then, because my entire project was on the geomagnetic sphere, you know, anyway. So
Yeah.
It was pretty handy. Because it was
And
on
they said,
and its relationship to hurricanes. They're looking into more relationship into earthquakes. So it's all very similar. Pretty great.
And they said the poles are going to switch, or it has switched already, the North and South Pole.
Oh, no, they haven't switched yet, but they are. It's moving more and more rapidly up to. It just keeps increasing its speed every year. So
they say it may not affect the existence of Earth, but it will change some things. But they said they switch every few billions of years or something like that.
Yeah, I don't know. Like, well, see, I read years ago that when it moves, when it gets to a critical point, it will shatter into like 500 poles. You'll have like 500 North Poles all across the world, and then it will come back together again, but it'll be the other way around or something, or it could be just reorientated. Like, it doesn't have to be like, the North Pole will be somewhere else rather than where it is now. But I don't know if that's true. It's just something I read in like the New Scientist back in the 90s, I was like, yeah, that's true. And then like, is it true? Is it still true today? I don't know. I can't keep up. Just to tell you another article, let me see. It appears there's a telescope in New Mexico somewhere. That's the one in the south. And then there's another one, Las Campanas Observatory. That must be the one in New Mexico.
Where is that?
And then there's another one. Yeah, then there's another one from data which is completely taken. There's a Northern Hemisphere telescope anyway, and I cannot tell you its name. Something angels, I think. Something to do with angels. But look it up anyway, the STS telescope. So there was that. Yes, so the point I was making was, with all of that information, and then I was also listening to this other guy called Bowden, and he said either the Earth is not moving or Einstein is right. This was the thing. And I was thinking, well, there's Airy's failure, which says that the Earth is not moving, according to some people, and there's the Mitchell-Samoria experiment. So I was like, well, okay, obviously Einstein's wrong. And then I was like, no, hang on a sec.
Got frozen.
Okay, point I'm trying to make is that there was this guy called Michael Bowden, and he said that either Einstein is right and the Mitchell-Samoria experiment shows that the speed of light is constant, or the Earth is not moving. So I thought that's valid logic, isn't it? Because it takes relative motion, and if there's no relative motion, then you're not going to see any slowdown or speed up of the light. So it make perfect sense. So then with Airy's failure seemed to suggest that the Earth wasn't moving. So thought there's two pieces of evidence in favor of the Earth not moving, and then you could probably explain most of the other things to do with relativity. Like I said, light bending doesn't have to be space bending. Dark matter can exist without relativity. That's fine. All of these things, you could kind of get around them and say, well, okay, it is a massive coincidence, but it does look like, you look at the Earth, right? And the way there's no time dilation on the surface of the Earth, despite the fact that different parts of it are spinning at different speeds. And the reason why that is because the Earth is not a sphere. It's an oblate spheroid or some, so it's like, it's just the right shape that it cancels out all of the time dilation, which I think is incredibly fortuitous. There's probably a physical
the life.
Why that is.
Life to yeah.
But so I just thought that was really interesting, and so there is the possibility that you could have these incredible coincidences, but ultimately it seems to me now that the way what is it that Sherlock Holmes says, like, if we eliminate the impossible, or the whatever remains has to be true no matter how implausible it is, kind of thing. But it's slightly different to that. I think it's like because let's say you have It's just, I think even Einstein said it himself. It's like whatever fits. It doesn't matter how implausible your theory is. If it fits the evidence, it's correct. That kind of thing. And I think, like, because looking at it, it seems statistically improbable that the Earth is not moving and Einstein is correct. And yet we have all of this evidence for Einstein being correct, and we have Airy's failure. So it's very improbable, but it seems to fit all the evidence to say that, yes, Einstein is correct and the Earth is not moving, which is it's still a pretty radical notion. And perhaps you would disagree with me. It's perfectly, perfectly okay.
No, what I am coming, I think I am very, like I'm saying, in terms of confidence, I kind of measure these kinds of things, give a certain percentage. So I am probably about 80% confident about all the things I have done, right?
Yeah.
And when I look at from other theories, even the top theories, they are less than that. So but I had to you have to still prove it, because I come from a very simple principle of Helmholtz decomposition. Everything is built from there. Yeah. You know, there is no assumption. So when I built, and then I can correlate with, try to combine, falsify with my observation, it actually passes all the tests so far. I mean, there are a lot of things, but the important thing I come.
But that's yours particular theory, is it not?
Yeah. But the two important things.
I'm talking about a much bigger issue. Like this is, I'm talking about isn't even my theory. It's just stuff that I've heard other people talk about.
But I want to build up
on that,
get to
rather than your opinion on your theory, which is like probably you're the only person who fully knows how that works.
Yeah, but the thing is that I want to develop such a way that I say, I'm not saying that I can explain all of it, but I want to develop such a way that one step at a time, whatever I explain, it makes sense. And then I move on. I don't go say, I'll explain all the things, black holes. I don't claim that. Because I have to still prove a lot of things. There are a lot of things.
I'm not asking you to, but what is your opinion? Like, just like put your own theories in the back burner there, and just like, what do you think of that issue? I suppose you'd need more time to research it. Is that what you're saying?
Yeah.
Okay. Yeah.
And also, two important things I come up with: the equivalence principle and correspondence principle. Equivalence principle more like Einstein or astrophysical level, whereas correspondence principle is more like a quantum. So I'm calculating that. I have, like I say, there's a way to calculate from the 4-vector time matrix. And when I do correspondence principle, I find a very surprising result.
Right.
The surprising result is that really correspondence principle, people are used, right? The non-equality, non-locality, things like that. Really the correspondence principle, when you put the light, see, you have to use the speed of light, speed of sound. I put that, what is the maximum possible? It's 1/4 of a mile, which means our PDP circuitry, which is like a functor or the function, the clockwork works only within 1/4 of a mile. Outside of that, the correspondence principle doesn't apply. It's a very important thing. So what connects the outside surface is a functional, like time, gravity, or something else.
Yeah.
Okay, which means that it's non-linear. The time is not linear. It's linear only within that 1/4 of a mile, that correspondence. So the Hamiltonian applies only within the region. So how does quantum entanglement occurs with the distance of light? It's a totally different thing. It's not what they're saying. It cannot occur like that. It's totally because of the functional. Yeah. So the whole thing changes. See, they're saying, okay, the correspondence principle says that from the Schrodinger equation or the Hamiltonian, that you can apply to from light years, from here to another light year, some black hole or something. Yeah. And it can quantum entangle with black hole. It cannot, unless there is a connection. And what is the connection? What is the functional? And that's where Alexei comes. My feeling, Alexei comes to the picture, like torsion field, elastic field. All this comes into picture.
Yeah.
So I think you have to change the whole thing. I think it's all.
Okay. So you even though you like agree with the fundamentals of the space time, and you still think there's like a lot of stuff out there that needs like
a lot of stuff.
Yeah. Oh no, I agree.
Same with
I'm quite big into string theory at the moment, and I think that's really interesting, and I think the mathematics is fascinating and really deep, and they still have a lot of stuff that they haven't figured out yet within that theory. So, I don't know. What's your opinion on string theory there?
Yeah. So the string theory, what I believe is that it doesn't have observables, proper observables. So I am developing such a way that I come up with the functional will be a vibrational string, and that you can observe. So the string theory still can be used, but you have to modify that. You have to modify. So all of the things cannot be used the way it is now. It has to be gauged or modified. That's my overall opinion. That even relativity, it has to be gauged. It's not gauged or modified. So you have to modify that. Relativity can be used. Quantum, same thing. Quantum is gauged already, but it has to be modified. Correspondence principle. So we have to do surgery on them, microsurgery on them. Then you can, that's why there is inconsistency between quantum theory and astrophysical and then relativity theory. So if you do all these corrections or modifications, you will see that they will start become consistent. I'm pretty sure. I'm confident about that. Quite confident about that. I think it's not, we don't have to throw away the whole thing, It's like throwing the baby with the bath. We don't have to do that. But we have to clean up the bath, so that the baby can be inside. So, that's my overall thing. So the equivalence principle and the correspondence principle, we have to, I have remodified and say, what are the limits of that? And using my theory, it can, you can quantify these things. Like I said, 1/4 of a mile, I'm calculating that. That's about the maximum. So the time is not linear. Hence, we have to look at time totally differently in terms of the 4-vector.
Yeah. Well, when you were talking about, did you freeze there? I think you froze for a second.
Oops, something happens.
Yeah, you froze for a second.
Yeah, it went off.
What I was going to say was you were talking about quaternions and such.
Yeah.
But see, the problem with quaternions is you have like, what is it, like the square root of a minus number and all of this stuff, like the way it's like it's just something that doesn't happen physically, like 2 minuses making you multiply them together and you get a minus, or what, you know what I mean?
Yeah, but my theory, it says that how you get out of that to get observable, to get real things, How do you get out of the imaginary to come to real? So you have to use these manipulations, gauging different things in order to get it from the imaginary to the real. So quaternions are there,
I agree,
but you can, but you can convert them.
You think they have to be converted?
Yeah, they will converted very carefully to get into real things, real observables. That's what I'm getting at. So I have like a flow chart which will do that. So it's like a feedback circuit. You feed that into the thing and you get some information or message and then you do these 2 loops, then you get to the real things, It starts with the imaginary, but you go through the loop. That's why you are, as a programmer, probably we can do that eventually. See, I want to reduce it to a level that we don't have to use too much programming, Like you said once, and I remember you said, I think I can quote that, and that's a very important statement you made. You can do most of it on a pen and paper. At one point, I remember you saying that, and you are absolutely right about that. That's what I have done. So what I want to do is, even our PDP, hot PDP stuff, most of it I have done. And now finally it comes to very simple things. And then you say, okay, we cannot solve that hot PDP. When you do the mathematics of it, there is no closed form solution for it. So now the only way is to pull the observables of it and then do computer programming. And also see, I also, even in the conference I mentioned, that if you do the experiments, it will take like 10 years, a decade or more. But you do computer simulation, you can do in a year or two.
Yeah.
So that's what we plan to do.
Yeah, computer simulations are so much faster. You know, in terms of then doing it by hand, obviously, but
yeah,
because you can do some
you need the
calculations per second. But I suppose the thing is, like, if you want to do a visualization, that's like very expensive in terms of, well, you know, it's time consuming, and it's also very expensive in terms of your computer hardware. It eats it all up. So can do, like, if you do a lot of calculations, it's going to reduce the you know, obviously,
so
but the issue is you need to know, like, I mean, obviously, if you have like unlimited resources, but it's good to be cognizant, like, you know, like, do I understand this fully? Am I, you know, should it be done this way? Because I remember listening to some of the ideas that you had earlier, and I was like, I think you were trying to mesh them with what I was doing, and I was like, because you were coming at it from a sort of a relativistic point of view. I was coming at it from a very quantum point of view. I just didn't really see the mesh. That was another issue.
So the thing I am doing is reduction process, you know.
Well, I think you were kind of looking at it from a what are those things? Fiber bundles and warping of space is very interesting concepts, but it's a little bit. Still is kind of a little bit out of my league. I'm not really entirely sure how to do that.
See, right now I am doing zero budget, zero money, mental simulation. You know, my mind is working like a supercomputer now, and I have mind is working like a supercomputer. I have simulated most of it.
Plug you into the machine. Get Elon Musk over there.
Yeah. Zero money, you know, no, without money and simulating. And, you know, I said there is no time, there is no money to do that. So this is the only way out. So let my mind work that way. And when I do that and simulating, that helps me to simplify a lot of things. And now what I am coming up with is a simple, see, you need an algorithm. Otherwise, you cannot, if you don't plug in an algorithm or something, you cannot do your computer simulation, right? So I have come up with the algorithm and a flow chart, and that's much closer to the syntax. I'm almost writing a syntax for it, some kind of a weird logic syntax that's translatable. You know, even that I have come to, you know. So everything else I have eliminated, you know, because there's no time. We don't have money to do the programming. There is no the programming itself is very cumbersome to do that. I mean, you have showed me some programming. We can probably do that, Python and all that. But I think my thing will come to very simple things that you can actually.
Yeah. No, but I think what you're suggesting to do in general was like a lot more complicated than what I'm doing.
Yeah.
It would have been like a couple of levels above, and I would just I was too,
now it's
you'd want to make it like a lot simpler for me to.
Yeah, much simpler. That it comes to very simple, basic syntaxes. You know, very simple.
Well, if you're going to supply me with the equations, you know, these are the equations. You know, plug them in there, and I could do that then. Because you know the way we worked on stuff where I had like, what was it? We were working with the. I'll slip my mind now. It was like an old thing. Yeah. We had the balls in the thing. It was like a grid, modular. Hang on, it's here on my computer somewhere. You know, it's a famous principle. Like Euclid or some. No, not Euclid, but it's on my desktop, I think. Prime numbers. We did a lot of stuff on them.
Oh yeah, prime. Oh yeah, prime. Yeah.
Factorization, prime factorization.
Factorization, yeah. Okay, now, yeah.
Well, actually, I'm thinking, you know, the way that I showed you that diagram earlier with the graphs and it's all interconnected. Yeah. Want to do more stuff like that?
Yeah.
Using, you know, multi-dimensional shapes, and then also I'm getting into a lot of other stuff to do with QCD, quantum mechanics, just sort of simple stuff, and then unifying all of those, and then bringing relativity into it, but just on a very simple level. And I think, like, if I form that kind of foundation and maybe then just hand it over to you and say, you know, like, I'm sure you'll have your own work going, but you might be able to say, oh, I didn't know what to do with this, you know. You might be able to take it to the next level. That'd be really cool. But so I think
that's one paper.
We might do that over the next while. Like, I could even like code it, you know, maybe take an hour or two and code some stuff.
Yeah, it's a good idea. A great idea.
And then
we should have that in a couple of weeks.
It's not going to take me long to kind of complete it all, and then maybe, and then, you know, then you might look at it and go, yeah, that's very interesting, but I have no, you know, there's nothing you can do with it. There's no further. And if that's the case, you know, that's fine. But I mean, it's not that.
Maybe you can see some connection.
You could assess beforehand, because if you think like, here, there's nothing I can do with this, and you know, then there's no need for me to go through it all, because it would be just a waste of your time, you know. So
I don't.
Yeah. What do you think?
Normally I don't dismiss anything, because I really think over and eliminate logically, and I say if there is a way, I should do it. You know, I see positive, try to see positive things. I don't dismiss things right away. And I have to argue in my case why it is not usable. You know, that's the way I look at it. Yeah. But I believe that your expertise, you have worked on a long time, so you know what you're doing. So it will be ridiculous for me to dismiss, you know, right away those things. Right. Many people do that. I don't agree with that. You know, like we send new paper, they dismiss it. No, I would never do that. Anything that's new, I will go over it many times and I will try to eliminate. Now, I may not understand all of it, so I'll ask for clarification. I just want to mention, I think I mentioned, but Christopher, you had a great presentation of your masters. I understood, you know, not all of it, but essence of what your masters is. That's really great work.
Great.
And, it has a lot of value. Yeah.
Thanks very much.
And you can apply. Yeah, sure. You can apply.
Yeah. Sorry, go ahead.
Yeah, you can apply it. You know, a lot of things I was thinking about. I think there are some applications. We'll talk about it later. But I think your spacing we'll have more things, because when I'm writing the book with manual, maybe you can use that book. I don't know. We'll see. But I think it has a lot of space. I mean, the astrophysics thing, and we are all coming. I am always interested in astrophysics. Yeah. So I'm glad that Manuel has done that. He's a professor astrophysics there. So it's quite, he has worked on it for 20 years or so. So I'm quite happy that I am with him. And then we can all work together on that. And I want to see the connection between quantum and the astrophysics, you know. And then once I write this paper, the review too, and then the OJPS, you know, right now the review process, the first part is over, the second part, the big review is going to come now. I think by hopefully September, October, it will be published, and then, you know, that paper will help to do the next step of programming and then experiments. And also maybe Emmanuel comes, he can do some of the experiments. We'll see. You know, what I want to get it is a real thing, you know. But the theory is important. What I did that, the theory is important because, you know, there are a lot of questions hanging around questions about quantum mechanics, about Einstein's thing, when they have assumptions. And I was looking into Schrodinger equation Hamiltonian. What are the assumptions? See, it's not that clear. What assumption is that? But when I was not sure of correspondence principle. When I went through the correspondence principle, it immediately struck me. Oh, that's it. And the same way,
equivalence principle. I know the other one that you were talking about, the equivalence principle.
Yeah, equivalence principle. I'm glad that you actually mentioned one time, and I see sometimes when you tell it, it makes more clear to me because you are thinking the same way. All others they talk about. I have attended so many classes, some classes. I have not attended too many physics classes, but they talk more in terms of they're not broken down. But you are thought about it. You are broken down. You come to with simple things. That strikes me. Many of the points you and Emmanuel talk about things, even Manuel, that strikes me because that's the key thing. You're hitting the real point. So I'm glad that I'm with you because a lot of the understanding. You need bullet points, key points, and I think you have it. You and Manuel have it. It may differ from our thing, but that's important for science.
I
you have to have a independent.
It's good to be understood, like even if you disagree with the person, as long as you could understand them, then you know that you disagree or agree with them. And that's an important thing. A correspondence principle, though.
Correspondence, that was difficult for me, but now I understand correspondence is the quantum, the simple way. Okay. Is more complicated than that, but I like to break into simpler things, simpler concept. Although it may be a little loose, I think it's understandable. I like it better, So what I'm saying, correspondence is like the quantum principle is for very small distances, right? Like Planck distance or subatomic level, right? So it really applies to the quantum thing, the Schrodinger equation, wave equation applies only to that subquantum level, subatomic level, right?
Absolutely.
Maximum atomic level, right? Correspondence principle is that takes it from the atomic to the larger mesoscopic or higher things. That's what correspondence principle is, basically.
Well, wait a second, though. This idea of like a photon going through one slit interfering with itself. That's like a wave thing, so that's got to be.
That has to be correspondence principle.
Right.
This is a mesoscopic level. See, that's the problem.
Is that not on a smaller scale? Like, is that not supposed to be on a Planck scale? Or I guess
no. When you're going to slit is mesoscopic level. I mean, you have millimeters or centimeters. We are not talking about.
Have you read the original paper that experiment is based on?
But even that, any measurement has to be greater than Armstrong level or anything greater than, it has to be few thousands of a millimeter or something like that. It cannot be more.
Yeah, but I was talking to what's his name, John, and me and John were arguing about this, and I think John was saying that that there was, oh no, maybe I was the one saying that there was no slit in the double slit experiment. I was hearing someone talk about it. It might have been someone was saying it anyway. I didn't come up with, but so I might have it wrong. But that they didn't use a slit because what they used was magnetic fields. So there's a magnetic field, and the particle can either go right or can go left, and it seems to go both ways. So it's the double slit experiment is not like an actual thing with a slit in it, because the particle would just run into the flipping wall. Why would it go through either? Why would it choose either way? It would just, most of the time it would just slam into the piece of paper or whatever. So I think it's an actual field, and it's choosing to go one way around the field or the other, and that is the split that it's taking. And the results seem to suggest that it's going both ways all the time and running into itself. So that's consistent with the result,
Yeah. Sabin Hossenfield has done this. Then one guy called Tony Yuan. I think you may be seeing in research, a guy from China, Chinese Academy or something.
No,
He's come up with a new thing.
Yeah.
You know him?
No,
you know his work, right?
No.
Tony Yuan. He has put lot.
Tony Yuan. Okay, I'll check him out.
Yeah. Y-U-A-N. Yuan. Tony, T-O-N-Y.
Gotcha. Yeah, I got that. Tony Yuan. Right, very good. Yeah. And
so he has all new thing. He sends me a lot of these things, and he's refuting about all the things. And he has done a whole new modified Newton thing, a whole new thing. And he, they are very good in mathematics. The many of the Chinese. So he has done good mathematics. But I have some questions about that. I mean, his mathematics is really good. I mean, it's very strong mathematics he has done.
Yeah.
No problem. So see, I take it a pinch of salt. See, I work with people from one side to the other spectrum.
Yeah.
Emery Taylor, he's totally falsifying everything. Yes, I had done 1 or 2 papers with him now.
Okay. Okay, you froze a bit there, but yeah, I can see what you mean. I can respect that.
Only Galileo is remaining,
You froze there for about half a minute.
Yeah.
Emery
so what I'm saying,
falsifying
Emery Taylor.
Yeah, I know
everything
trying to falsify the Einstein relativity stuff, but what else is he going on? Because you really want
the next one.
Yeah. Go ahead.
Quantum level about space and time, about space, and the Newton thing. He has false. See, he has very good arguments. No question. Like a lawyer, it's a very flawless argument he has.
Yeah.
But he want me to do the mathematics, of discontinuum. You come up with the discontinuum. I think my theory will not come to that. Somehow, luckily, I think it will fall in. It will, because I'm using the gauge algebra I'm using. That is very powerful. It's actually a Jacobian. It's like first differential. When you're discontinuum, see, the good thing about it is most of the calculus will not apply. Second order calculus cannot apply if it's discontinuum, because calculus requires continuous function.
Yeah.
And if it's not continuous, so that's why correspondence principle comes into picture. My feeling also, before I forget, the slit experiment has a lot to do with correspondence principle. People are done so many millions of people almost have done on the slit experiment. Everybody gets into a double slit, right? Any physicist get into a double slit, and he has his own vision, complete analysis. But I think everybody has missed one important thing called correspondence principle. I think that is going to answer the question, my perception. The time is non-linear. And you use a 4-vector time matrix. You analyze that, the non-linear time, I'm sure you can solve the double slit experiment. I mean, it's not easy. It's going to be very complicated, more complicated than what. But at least I got the idea, and I think I am on the right track.
Yeah, I have still got like a bit of trouble conceptually with parts of Einstein's theory.
Yeah.
Just the time-space side of things, like where the way certain things aren't happening simultaneously and stuff. And the thing that really got me actually, or made me a bit, and I'm accepting of the theory now, but I'm still a bit puzzled by, do you think this idea of like, I'd have to go back and look at it, but it's basically Minkowski space-time, and you're doing like triangulations in space-time. So you're saying you're like taking angles between events in space and time, and something about that just seems very fanciful to me. Like, it's cool, but I just find it hard to believe that it's right. But it must be, I guess, because
that's what he see. One of the things Emery Taylor, and when we published, if you look at the rethinking, I published along with him, right? He had 2 other publications. He talks about Einstein's tabletop experiments and also the the Lorentz thing.
Yeah.
That he has analyzed that. Very simple analysis is given, and seems to be right that actually what he talks about a time dilation is not correct.
Really?
It's because he's talking about 2 different things, and he's comparing apples and oranges. He comes to eventually to comparing apples and oranges.
Yeah, is this special relativity or general relativity?
Yeah. So you should read our my paper with him, and also,
you know, there's people who say like, well, maybe the measurement problem in special relativity is not real.
Yeah.
But and it would have to be real in some, like, general relativity still, you know, the measurement problem there is real. Like the if you go out from the planet, there's going to be a noticeable time dilation. But maybe if you're going laterally across, that's just a measurement error on your clocks. But who knows? I think it's possible both are.
So I respect all the scientists from Galileo, Newton, Einstein, Schrodinger, everybody, right? Maxwell. But I think I have to take it with a pinch of salt. The way I look at it is, they have done something good. So take out the good thing. What is a good thing I like about Einstein? Metrics. He introduced about metrics. I like the metrics. The idea is that
the tensors, like, or just why particularly the metrics that you like?
Metrics is like, you have ds square is dx square plus dy square plus dt square, c dt square, right?
Yeah.
Minkowski space. The Minkowski space. You are splitting up into that, right?
Yeah.
Then you say each one is shaped by the matrix. In front of the dx square, there's a term, right? A matrix term. Each term there is a thing. So it is dilating. It kind of, the matrix is changing that space.
Yeah.
But the space on the dx, on the x-axis, it's changing the space on y-axis, changing the space by z-axis, and changing the space in time axis. Essentially, that's what he says. See, you have to break it down. See, I like to break it down to simplest level, you know, and understand it, like Helmholtz decomposition, like that. And people don't do that. That's where the problem is coming. So you have to come to first principles, and then what is correct? I question that. Like Newton, you come to that. F equal, he says that acceleration is second or differential with respect to time twice. Differential with respect to time is velocity. The second derivative is acceleration. Yeah. Now, when you come to gravity, where Einstein comes is gravity and acceleration are the same according to him, the inertia.
Yeah, it's true.
Now, but yeah, so that's a problem, because how can you equate that? Now, there is a way to equate them. So you have to rework these things. See, their concepts are good. The way I look at it is, the concepts of all the same, even Maxwell is good. But the actual things, you cannot take it literally like that. You have to modify them. That's why I look at it. Even Einstein, you know.
I find you know, acceleration and gravity, that seems correct, because when something's falling in a gravity field, it's accelerating.
Yeah. So what I see, you should read my couple of papers, that configuration of the thing, discontinuum. In those papers, the last 4 of them, I talk about gravity itself. From our theory, I can understand gravity, and the gravity actually is what? And I had to work on this word. Gravity actually is differential density. So something is falling. Suppose I keep my hand here, right? It cannot fall any further if I put a ball, right?
Yeah.
If I remove my hand, and this person from Hungary, she has written from her daughter, is saying that there is nothing under it. That's why that's falling. So if I keep it there, the ball will stop here, right? If I move my hand, the ball is going to fall down, right? Yeah. So that is described as gravity, but gravity really is stratified density. So if I have something that is denser, density matter is higher, it's going to, than the medium that's falling, it's going to fall down, keep falling down until it hits a thing that has higher density matrix. That's what gravity is, really.
Wait a second, though. Okay. I've heard a defeater for that, which is that, if that's the right word to use, I'm not sure. But you know, like, let's say you have this bottle, and it's dense, you know, it's more dense than the air beneath it. So why isn't, but it's not as dense as this this box over here. So, you know, someone says, why doesn't it fall that way? Because this, you know, it can fall any way. If
No,
gravity
if it's
is density, then why does it fall this way?
why doesn't follow this way?
Why does it fall straight down instead of go off to the left?
Okay, so that's where stratification comes into picture. Stratification, stratification of air, things like that. So the gravity is okay. That's one I think I have and calculate that density and matrix is not same as density. They are different.
Oh.
Density matrix is different from density itself. It's not that it's denser.
What is it then? I'm not sure.
Density matrix is a matrix of, so you have to look at each point in that one. Like your bottle, right? That topology matters. So the bottle, right? Bottle has.
Yeah. So you've slightly frozen again.
If you see the density. Oh, okay, sorry. So your bottle is like this, right?
Yeah.
Bottle is like that. So if you do the density across is non-uniform, right?
Yeah.
Just high dense here. And then when you go into the bottle, it's low dense again.
Yeah,
right?
I agree.
Because air. So it's a non-uniform density. So you have to look at the density matrix. So that's why it's complicated. But your point, I was thinking later on about that falsification. Okay, why doesn't it move this way? Why does it go this way, right?
Yeah.
Why does it go down, up and down? Why does it have a directionality, right? So that's the important point. I think I had an answer at some point, but I had to work on it. I know you need a more solid theory. I agree with that. More solid.
You don't go for this space-time metric, folding, or are we frozen again?
Oh.
Do you go for the space-time, contraction? I would call it more than it's folding, or warping is the wrong word, but it's a contraction, isn't it, of space-time?
Space-time. Yeah, I think you have to modify all those concepts because I believe in discontinuum. The thing is now it's not continuous. The space and time are not continuous. Oh, so they're like functors. They're functors.
You can't do Einstein's theory of manifolds and all that without a continuous. Is it differentiable space?
Yeah, but only like I said, that's why I differentiate between functor, function, and functional. So within the functor, right? Within the functor, something is function. Yes, you can do all those things. So you have to, suppose I have a bottle here, right? I have to break it down to different regions. So within that region, yes, I can use the topology, everything, the function.
Yeah.
What you said is correct because we need a functional relationship. And you have to, like the Mobius transformation, things like that, right? You can transform a rectangle into a torus, right? The Mobius transformation, right? Mobius.
Yeah.
They have proved it. They have proved now the complete. I mean, that's what they were working till recently, proving that they proved completely how you can convert a rectangle into this thing. So that's a complete theory now. It's a complete theory, Mobius transformation.
Yeah, I know that.
Yeah. So that applies to only certain region. You see that? So you have to break it down into each region. Like a bottle, you cannot take it as one thing, but you have to section it and say, okay, within that section, we can use the topology and everything. So like that, you have to build up. You have to integrate that or put them together. I think that's definitely required. So geometry in general should be looked upon that way. I believe that geometry has to be sectioned, and a particular topology thing applies only to specific region, and then you have to build up,
Okay,
so
well,
you cannot.
That is extremely abstract. That's
without that, that's why geometry sometimes doesn't answer the questions because you have to do this. I mean, you do that in your school.
Your explanation there is like very abstract. It's in the realm of like science.
Yeah.
It's like in the realm of mathematics and like abstract concept. Or I don't want to use the word abstract again, but like you know, it's definitely mathematical. It doesn't. It's not highly directly real world, but I mean, so you could say that of the other theories that it's trying to supplant as well. So, yeah. But no, I was going to ask a question like about you know, if you have your correspondence principle and you're saying that there's a quarter of a mile and then it stops, right? So that would be something that's not continuous, right? It breaks off. But what if I move like 1 foot to the left, or there's someone standing beside me 1 foot, and then their radius, I'm just assuming here, I've really no idea. It goes off for like a quarter of a mile. So there's like an overlap of between like an area where there is a radius and where there isn't. So then does that not become continuous again, I suppose?
The continuity comes from functional, the things that connects, you know, like the time or gravity.
Yeah.
So the functional is that connects from one functor to another functor. So you can think of that quarter mile as a functor, right? And another somewhere else, that quarter mile is another functor. The one that connects between the two functors is functional. For example, I explained this. For example, on Earth, this is not a problem. See, the functors, although I call functors, if you go into the theory, deeper into the thing, functors can be function under certain conditions. They are not different. They are the same, right? So functor is a more general thing that under certain conditions, they can become function.
Yeah.
So there is no problem with that. So the correspondence principle then extends automatically to over the whole Earth. You can think of that way. You have to prove it. I have to still think about it. But I think the correspondence principle probably applies. You know, once you prove the strictest aspect of the correspondence principle is only 1/4 of a mile. Now, if the functor is satisfied for the next functor with the functional, and the whole thing can be considered as a bigger function, then the correspondence principle now extends beyond 1/4 of a mile, maybe over the whole Earth. It can go to the, but you have to prove it.
Even if you take like a ray of light or something, I mean,
same thing.
It's going to be like much bigger, longer than 1/4 of a mile. It's traveling way faster. So
it can correspondence principle. I mean, there is nothing stopping it from applying the correspondence principle even to light years, but you have to prove it. It's not instant. It's not intrinsic. Intrinsically, only 1/4 of a mile, but you can prove it that yes, it can apply because you saw a functional that connecting, and the whole thing can be described by a function. So then the whole light year, Earth, and probably the solar system and the whole galaxy probably can be described by a correspondence principle. But it's not intrinsic. You know what I mean? It's not automatic. You have to prove it. The automatic thing is probably like 1/4 of a mile.
Well, now I understand when you say it's not automatic, but when you say you have to prove it, that's where I'm not sure I follow you there, because I mean,
you have to prove that say functor in general cannot be a function.
Doesn't it seem a little bit like, you know, we accept that space is continuous. We accept that.
That's not really true.
But we do accept it. It does appear to be continuous, doesn't it? Now,
that's not true.
No, I'm not saying that you're wrong or anything, but I'm just saying that it appears to our perception.
A lot of things appears that way.
Yes. Doesn't that mean that since you're coming up with a theory that is at odds with what we generally experience, it's kind of up to you to prove what you're saying? Would you say the onus of proof is on you more so than the other way around?
Yeah, but actually, quantum mechanics says space is not continuous.
Oh, good point.
Einstein says it's continuous, but quantum mechanics says it's not continuous. So I have some friends there.
Okay, true. Yeah, but what about string theory? Doesn't that deal with that?
Yeah, string theory. My feeling is that. Oh, okay.
Oh,
you are showing. Okay.
Yeah, I'm showing something, but I want to hear your opinion on that, because
string theory. Yeah, string theory. I like the string theory because one of the most beautiful theories ever made. Okay, mathematical theories.
Oh yeah, without a doubt, very beautiful.
And it connects. It, I even derived a separate theory which is very similar to string theory because I didn't know that separately. I called time matrix. I did that many years ago. I put it away somewhere.
Yeah.
And somehow they didn't publish it, but I don't know why I sent it for publication. It explains the pattern time. It explains everything, So what I say, I converted everything to time and time equation. Essentially come with the time equation, and you have like nth order time equation. And you solve that, you get all the time constants, which corresponds to all the frequencies. Now, string theory is very similar to that. So that's why I got attached. See, I did it everything differently, and then like Helmholtz, I did it of my own, but suddenly I found Helmholtz satisfies that,
Did you find?
So I said that okay.
String theory there is like, they're looking for a way to bridge the gap between general relativity, let's say, the continuous space of general relativity, and the
Can you hear me?
Yeah, did I freeze? Can you hear me?
Yeah, a little bit, yeah.
Okay,
yeah, so now I can hear.
Okay, so in string theory, they were looking for a way to bridge the gap between the continuous space of general relativity and the bumpy kind of mad space of quantum world. And then they found that the string, like if the string is a certain size, it will just glide over all the bumpiness, and we'll just won't notice it, and so therefore it doesn't exist. And that was their way. They solved the whole issue, So string theory is correct. It's already solved those problems. So
problem is it doesn't have observables. There is no way to prove. In physics, you need observables to prove it. And string theory does not have any observables.
Yeah, but it's only not observable because it's so bloody small, right?
Yeah.
Not like
but the problem.
But in some of the theories of quantum mechanics and stuff, that there's unobservables which are you'll just never be able to see them because they're mathematical concepts, or they're like they're predecessors to what we observe in reality. So you just never see them, or they're too short-lived, or there's loads of reasons. But this particular one is a little bit, it's saying that like if you did have a big enough collider, the chances are you'd be able to find these things, but we're just not able to see them at the moment.
So the thing is that I think for to solve the problem of dimensions, I think string theory has this problem. But
too many dimensions.
Kind of I keep multiplying the dimensions. It goes to nth dimension. So in order to solve that problem, I think the functional. It retains most of the things. I'm not saying string theory is wrong in that one, but it modifies. It applies to as a vibration, as a fiber.
Yeah.
That connects one functor to another. So that's where the string aspects come.
That's the bit I don't understand at all. Vibrations connecting functors to one functor to another. Like I'm just lost at that point.
Okay, you have. Let's say you have a ball here, right? Another ball here, right?
Yeah.
These two balls are connected with some strings. That is what a vibration is. But it's not one string, many strings connecting them.
Yeah.
Okay. Yeah, it's connected by many strings they form vibration essentially.
Yeah, I get that.
The simple way. Yeah.
It's pretty simple.
Dynamic.
Yeah.
Yeah, it's simple. But it's not static, it's dynamic. That's the only difference.
Meaning if you pull the balls away, the strings get bigger, they get longer.
Yeah. And also they vibrate. They don't stay in one place.
Yeah.
They move around.
And what are they? Are they it's between one space time point and another.
Almost like a field. That's what a field is in a way.
But this is the ball at time 0, and this is the ball at time 2, and they're connected by vibrations.
Yeah.
Which are the atoms of the ball stretched through time.
Yes.
Yeah, you don't seem too sure.
And that also, that's one aspect.
Yeah.
That's true. What you're saying is true from the point of view of time domain. Okay.
Yes.
Space domain also, it exists like that. Space domain, suppose in one period of time, let's say time is constant, like the time equal to 1 minute, right?
Yeah.
So you have one ball here, another ball. That's what I'm talking about first. Okay.
Yes.
So one ball here, another ball here. They're connected by these strings, and many strings, which are vibrational strings, fiber strings. Okay. So that's at one point in time. Now you can change that to from space domain to time domain. Then what you are saying is also true. That one ball is here at time 0, right? Yeah. And the ball is moving to another place in time equal to 1 minute, for example, right?
Yeah.
So then how are they connected? Again, they are connected by these vibration strings. But it depends. In space, when you have these, the vibration strings become gravity. Okay? In space domain.
Yeah, yeah.
Okay? In time domain, they become time. So the vibration strings are not the same. In space domain, they are gravitation strings, you can say, right?
Yeah.
And then in time domain, they are time strings.
Yeah, yeah.
They are not the same. But what I'm saying is, in general,
they are the same, but you're just looking at them differently, or they
different.
are different.
Okay. So what is the difference? The difference is that the direction. In one direction, they are time strings. The other direction, they are gravitation strings. This is a little more advanced, a little more quirky, a little more difficult to understand. But I think I can prove it. You need a little more quirky thinking to really, much like the quantum mechanics, that you are the quaternion, for example. It's kind of quirky, but it's not wrong.
Yeah.
It could very well be correct, right?
But isn't gravity meant to be isn't gravity meant to be a warping of space-time, and now we have it as strings?
Yeah. I think, okay, I do agree that we have to explain, because Einstein thing is important. You have to explain the warping of space based on this one. That I am thinking about. I think it can be explained, but it's a little more involved,
So why do you think there's this bifurcation of like the viewpoints, where one side's going off into warped space-time, the other one is talking about these vibrations? I mean, why split? I mean, surely there was a point in time where someone
there's a connection. There's a connection.
Yeah.
They're not obvious. It's not immediately obvious. So you have to explain them. Normally, if it's not immediately obvious, you have to explain them. There has to be strong theory, quantification, as well as argument. I believe in that. Now, sometimes it takes time to explain it. But in my mind, I can see it, but I should be able to explain it. I agree with that. So let's go with that. I think I may not be explain everything, but to start with, very simple way, the vibration and gravity. What's the connection? That's why I say the stratified density. The density matrix. The density matrix is not it's not uniform. Even in the bottle, you look at it, you plot that the density matrix is not uniform. That rings a bell. That rings a bell. That there is a non-uniform distribution of density matrix. That's the first thing you come across.
Yeah, of course. So you have a greater concentration of strings in that area, vibration strings.
Why is that? Why is that?
Because
in the bottle you look at abstract. You look at abstract a bottle, right? I'm not thinking anything. You abstract me. You kind of eliminate everything else and look at it from a mathematical point of view. Okay, that's the way it is. Why is there a non-uniform density? It's not we made it and everything, humans, right? But it is there. So why is it dense here? Why is it become less dense another place? Why is it that? There should be an explanation for that. I think there is an explanation. There's an explanation. See, that explanation will help in explaining a larger thing. Okay, this is one of the great things scientists always have done. That's why they were successful in explaining. But I think this is much more deeper. Like Randall syndrome. You remember that Randall syndrome, non-uniform distribution of gravity. That's a very fundamental thing now. Lisa Randall. Harvard University.
Yeah.
Okay. That's a very fundamental thing in explaining about gravity. Okay, it doesn't explain everything, but that's one of the breakthrough. So like that, why is there a distribution of density? What makes the density non-uniform distribution? So you have to think from a more fundamental point of view, like the bottle, for example. What makes it like that? What makes it concentrate in one place? The same thing as vacuum. Okay, vacuum is the same thing, right? If you look at the vacuum, the speed of light, I put it in our paper also. The speed of light is true only in vacuum, constant only in vacuum. Let's see.
Yeah.
In the superluminous thing, it can be faster than speed of light. In the matter, it's less than speed of light, right? What differentiates that? It's the same, very similar principle actually applies here. So what is that difference coming into? That's why I call. Did you freeze?
Yeah, you froze.
Can you hear me? Yeah. Okay. Now can you? Okay. That's why I believe that to understand this non-uniform density, you have to go all the way to lattice, all the way to prime factorization, all the way to magic square. Okay. Otherwise, probably you don't need it. But you will be surprised. Sometimes you have to go to that level to really understand it. So what is happening? Unfortunately, or fortunately. So what is happening is that I described that in one of my papers. The 4 papers, in those 4 papers, many other things are there. So they are already published. So I use it. I can now use it at random, but you have to go into that. So I describe that more in detail.
Have you ever used you've used Photoshop? Yeah.
Very rarely.
Okay. Well, there's something called something in Photoshop called I don't have it anymore, so it's
okay.
It's hard for me to look it up. I used to have it, but they made it prescription or subscription. I mean, I don't have the subscription anymore, but it's some sort of lattice. Typical, if you look anything up on the internet, it's never the thing you want. Just gives you a load of lattices.
Oh, there's so many. Yeah.
It's some sort of selection tool, like a lattice select, but it has a funky name, like puppet select maybe, or something like that. Anyway, it's just like it's a load of lattices that get like more dense in certain areas, and the lattice more dense in certain areas and like more sparse in other areas.
Yeah.
And it looks really cool. It's very
it's a random selection. So random. See, but the reason behind it, the mechanism behind is the prime factorization magic square.
Simply. Well, yeah. I mean, I don't see that now. Prime factorization. Why? How does that get you there?
Okay. Yeah. So what is happening is, let's say one space as very simple from numerical point of view. Okay. Now we have to convert it to physics. Suppose I have a number of 26, right?
Yeah.
So now that actually likes to prime factorize into 13 and 2, for example. Okay. It's a fundamental principle. So.
Oh, sorry.
So it splits.
Saying that dimensions number 13.2.
Yeah, 13 times 2 is 26, right?
Yeah. True.
So 26 splits into 13 and 2. Factorizes.
Okay. Yeah, I get it.
So it factorizes to that, which means what happens is, I described that that's why gauge unitization is important, but eventually the gamma factor, which is, I'll call it the gamma factor, because signal to noise ratio, essentially gamma is signal to noise. Okay. Yeah. So what happens is, if you split something, right, it will have higher gamma. I'll just call it gamma from now on, which refers to signal to noise. Okay. But I want to say the whole thing over and over again.
Yeah.
So,
yeah.
Okay. So the gamma of 26 splits into gamma of 13 and gamma of 2. Okay.
Yeah.
So the gamma of 13 and gamma of 2 are higher than gamma of 26. Because suppose I have 0.5, I split it up, I get 0.8 times 0.6 or something, right?
Sorry, what? What was the last?
If I have 0.5, right?
Yeah.
I split it up. I can get 0.8 times 0.6 gives me 0.5, close to 0.5, right?
Oh, because
8 times
48.
8 times 6 is 48, which is very close to 0.48, right?
Okay, yeah, fine. Okay.
And 0.8 is both 0.8 and 0.8 is higher than 0.5, right?
Yes.
0.6 is higher than 0.5, right?
Oh yeah.
So normally when I split it up, I get a higher gamma value. Right?
Well, no, but doesn't that works for values that are smaller, right? Because like this.
Yeah.
Like, but the other way it'll be they.
Yeah, the other way it works the other way.
Right.
So it can either. So my whole point is it can either split it up or it can combine, right?
Yeah. Okay.
In general.
Oh yeah, that's cool.
So that's the whole idea behind it. Okay. So it doesn't remain the same. You know, from the theory of prime factorization, why does it split up? Because it can now form a magic square, and magic square itself, it doesn't remain the same. It will split up because magic square is not a perfect symmetry. You see that?
Yeah.
If you have magic square, you probably have seen this already. It's not a perfect crystal symmetry.
Yeah.
So it breaks it up. It breaks it up. It is only a transition point. A magic square. It's nice. It can get a good symmetry, but it's not a perfect symmetry. So it splits it up. So it doesn't have a choice based on this principle. It will have to either split or combine all the time, right? In general.
Yeah.
Okay. You can accept that qualitatively, and then we can actually now crunch the numbers exactly later on. But we don't worry about it for the sake of argument. I'll just say at any time it can either split or combine. Is that acceptable?
I mean, yeah, like I say, it's very abstract.
Yeah, but based on what it is there, okay, what it is there, it can either split or. So we don't worry about the condition,
right?
But we can go into the details later on, and then we can figure out.
Numbers represent what points in space time.
Yeah. So suppose I have so many 26 atoms together, right? Or 26 entities, particles together. It like split into 13 and 2.
Okay? Yeah, I get it.
Okay. So which means that, you know, without going to all the quantity, we can work out the quantitative details, but for the sake of argument, I am not going to all the minute details of the, of the numbers. But what I'm saying is I get a concept from there that at any point it likes, because of the particular configuration, it likes to either split or it likes to combine. Is that acceptable?
Yeah, but how do we, if I'm looking at like, I don't know, 13 grapes on a table or something, or 26 grapes, you know, I mean, the universe could split that into like 2 sets of 13 or like just 2 sets, or which do have 13 in them, or it could like split them into like 14 and 12, or do you know what I mean? I mean, you know,
but if it's factorizing, so anyway, it like to split, right?
Okay.
That I'm trying to, it like to split. Now the 14 and 12 could form probably a magic square, so it may like to do that. Right?
Yeah.
So some symmetry. It likes to form some symmetry. That's the basic principle. Like Noether's thing, but it's more generalized to Noether's thing that nature likes to form some kind of a symmetry. We don't know exactly what it is. Could be magic square symmetry, some symmetry. Okay. It may not be perfect. It doesn't need to be isotropic. It doesn't need to be what you call as the homogeneous. It doesn't have to be what you call isotropic. What is the other one? Symmetric even. It can form anti-symmetry even. Okay. So nature doesn't like the same thing. It likes to either split or combine all the time. Okay. Even our cells, we can go back to our cells, our body cells. If the body cells does not split, we don't live. You know that?
Are you talking? You're talking about splitting. Are you talking about on a realm outside of human perception, like in a?
Oh yeah, exactly.
Oh, okay. Jesus, Rajan, you have to say that. How am I supposed to know what the heck you're talking about?
Yeah, I'm sorry because I got used to it so much time. I take it for granted. Yeah, but I should specify that. Yeah, it's outside the human perception. That's true. Conscious mind, you have to. I mean, I talk with Emery all the time about the consciousness. He differentiates that outside the human physical reality, and I think he has a very good argument. I mean, I cannot disagree with his thing. Yeah. But there are some things I
know what you're saying is like I think you've been talking about this for about a year, and I haven't been following
them out right away.
I keep a little bit, more.
Important.
Huh? Now I understand a little bit more, a little bit. So it's funny, but that is funny, yeah.
So I like to look at each things like relativity and what you can pull out. There are some good fruits in there, good things in there that we have to retain. But there are a lot of other things that we cannot use. So that's why I look at it. It's like taking a package and looking to a package and what you can keep, what you cannot keep. Like some are trinkets, some are trivial. So I differentiate between trivial, special, specific, and general. The two different things. That's how I classify them. So you classify accordingly, and then so you take the good specifics, good specials, and good general, and throw out the and then clean the trivialities out. And there are a lot of trivialities, unfortunately. But in any case, that's classification of theories. But what I'm saying is that we can accept, and we have to accept this. I mean, only then after that I will go on. Can we accept that that nature likes to either split or combine all the time?
Yeah, I can accept that now, especially when you're talking about I assume you're talking about like particles splitting in space-time and coming back together again.
And then combining at some point.
Right? Yeah.
That goes all the time. Now, I'm not going to use too many things. So I want to minimize the number of things I use, like this one, description or whatever you call it.
Yeah.
Or concept. You can say it's concept. So I like to minimize the concept I'm using and use the minimal concept to explain everything. That's I believe in that. So let's say only I'm going to use that for now. So nature likes to split or combine all the things. And I have to explain everything from that point of view. Yeah. So for example, how do you get a non-uniform distribution of density or stratification of density, you can call it? How do you get it from this principle, this concept? So that's a big challenge. Yeah. Eventually, you have to be, not only describe that, but I have to be able to quantify that later on.
Would you not find? Can I ask you? Would you not find something like a Riemann surface to be a bit better for that, with the cusps, and the Surely that would be a bit more useful.
Yeah, you remind me of your Mexican hat.
How about this, right? How about like a more physical concept, because the Riemann thing is very abstract. What about if like time, rather than a river, is like a stream of air constantly blowing through and across a hyperdimensional surface, which is space, causing it to essentially dry out in some way. So it's like losing some energy through the process, which is like, and causing it to shrink, and therefore causing it to crack. And then, so the matter, in a sense, are like loads of tiny cracks, which then leak out energy. The energy is the matter, and then they form stars, and because of the shrinking process, then it's pulling in the space around it, causing the gravity. something like that.
That's a good way to describe that. I mean, analogically, very similar to what John was describing about what. So the thing is here.
This, look, this side. Yeah. I've had that idea when I was like 7 or something.
Wow.
Oh. This was the. Hang on, do I have the picture? This.
Yeah.
This is what I'm talking about. I've been bringing this up a lot when I was, you know, the idea of things cracking, and it also looks like electricity, right? And but so initially this was all uniform. It was all one thing. It was wet, but then the wind has dried it, and the sun obviously, and then it gets, you know, it contracts. So yeah, like when I say, you know, that was something that I saw when I was a kid, and I thought, you know, there could be some unifying principle at work in terms of what we see here and the similarities between that and, you know, what we see in the cracks in the veins of leaves and electricity and so on and so forth, lightning, and, you know, and then like extrapolating further to create a larger theory out of space-time. But, you know, that might be an interesting way to go.
Yeah, unifying principle.
Yeah, and look at the way you have so many like right angle turn, like there's a right angle turn there, and then the whole thing of like the wind blowing over the surface is some sort of vortex kind of right angle.
The main thing, I think, main thing underlining in this is identifying the mechanism. See, once you identify the mechanism, right, that's more physics, more scientific explanation, right? So we have to come up with the underlying mechanism. Once you come up with that, I think, like I say, everything is superfluid or supernumerous, right?
Yeah.
That we are thinking, and then you have mechanism like our hot PDP mechanism, which will differentiate that, which will produce these energy pockets, and then that energy pockets then can create particles, you know, quasi-particles and particles. That's the general mechanism we are talking about. So there is an underlying mechanism at work that produces these things. Okay, and then we have to, once you identify the mechanism, I think, you know, it has substance.
I mean,
you know, it has,
just running with this analogy, assuming this would be useful, I don't know, like if the ground here is would have to be space, I guess, or would it be math? Yeah, I don't know. Anyway, I suppose it's more just.
That's a good one. That's a good, I don't know, you know. I mean, those are the correct ways, I think, you know. So, I mean, you are proceeding, those are correct ways of thinking about.
You had ideas about erosion. Hitting, didn't you? And hitting in space-time and erosion.
Yeah. So again, there also you are talking about non-uniform density, right? You have a mechanism there that produces a non-uniform. What I am talking about.
This is exactly it, because this is non-uniform. Things are clumping together.
Space. So there is something. Yeah.
But
you have now
it's lattice-like, isn't it? Because it's broken into cells.
Yeah.
So it's like a lattice.
So my thing, what I'm talking about,
like functors connecting different, or is whatever's the you could say like the jewel of this broken up landscape could be another kind of functor of the
like your bottle. You can connect the bottle is very similar, right? Just the opposite of that. You know, bottle, just the conjugate of that. Whatever that region, right?
Yeah.
Is empty. The region, this wall is dense. Just a conjugate of that. You know what I mean? Conjugate of that cracked or parched soil. You know.
Yeah.
Very similar. So there is a unifying principle there. Also, you can use the concepts I was talking about. Nature always likes to either split or combine things, right? Same thing you can use. Now it's splitting, right? At another point, some rain comes, it combines into one slush, One big,
Yes.
right? All you need is a little bit water or rain, and everything becomes a muddy, all together one uniform thing, one whole thing, right?
Yeah.
Slushy thing.
Yes.
So you can see it combines. Depending on the mechanism at work, it either splits it up or combines all the, you know.
Yeah.
So then same thing happens with the bottle. So you look at different perspective. The bottle is a very similar thing. Something has combined it at the wall to make it the dense, that one, and then it forms that continuous thing, and that there is a hollow thing inside the topology. The topology is formed like that, right? So like that nature, like geodesic, like Earth, same thing, right? Earth is the same thing. It was probably different things, like.
Yeah. I think you froze again. It was probably different things before it was the Earth.
The theory of Earth formation.
Yeah.
Yeah, theory of Earth says that it was all one called UR. I think it's called R, something like that.
Huh.
It was the one big blob of things. Then it got split up, and
yeah.
it formed continents, different continents.
Pangaea, was it? Pangaea, the one big continent.
Yeah, it's called R, right?
I think there might be a couple of different names for it, but the one I know.
Yeah. Depending on Latin or Latin, Greek, depending on what they are.
I think they might have. I think they might have been all together, and then they start breaking up, and then they're gonna come back together or something.
Yeah. So they made into different continents because there's water in between. So I think they may have been like marsh gas, the methane.
But then the whole, the expanding Earth theory as well. Not to get sidetracked with your analogy here, but that I suppose space is expanding. But then the other concept, which is of course that if relativity is correct and all the rest, then who's to say that space is expanding and not that matter is contracting? So then matter is contracting. It's like, again, the soil that's pulling away from the rest of the place. So it's sort of drying up in some sense. That's just an analogy, obviously, but so it's contracting and it's falling into a hole essentially, or it's getting further away, isn't it? In a different dimension, it's getting like further away, while still staying the same size relative to each other.
So we are to always, in physics, that's one thing I will emphasize. As we go on, two things are important. One is observables, the other one is mechanism. You have to identify. Without that, there is no proper physics. It's not a proper theory. Right. You have to come up with a mechanism, underlying mechanism which operates. Then only you are, then you describe based on that. Yes, that's fine. And then you have observables that can prove it.
Well, I suppose even if you look at like the larger, I mean, this is continuing on, like just looking at the bigger galaxies with all the filaments, they are like the cracks, aren't they? Then you have the voids, which are like big lumps of matter that we were talking about earlier. So it seems to invert then on a larger scale.
Yeah.
Or become more solid as a kind of theory. So.
Yeah. So you are also describing an observable here, which is good. You are already pulled out a mesoscopic observable there.
Yeah.
That's a good thing. So that's what you need for physics, like that. That's acceptable.
Yeah. Well, there was
to start with.
I think there was a French guy who was making videos on Daily Motion, and he mentioned these voids, and how his theory was, I think, that dark energy or something was expanding the voids. It was a while ago that I watched it. It was something like dark matter being repulsed by dark energy or something and expanding the voids. And no one would listen to him. And then I think it was like 10 years later, some other guy in the US or came up with pretty much a very similar theory, I thought. And you know, his name is in Wikipedia, and this French physicist, poor guy, I can't even
that happens.
I can't find his video on Dailymotion to tell him, hey, look, your theory is more or less accepted now. Yeah.
Like Tesla, same thing happened with Tesla, you know.
Oh, but yeah.
Like,
Who knows? Yeah, very few people even knew that Tesla was responsible for all of the major inventions of the 20th century.
That happens all. Da Vinci himself have a lot of ideas, but he's credited with something, but he's known as a painter, you know, as an artist.
Who's this?
But Da Vinci, Leonardo da Vinci.
Oh yeah, of course, yeah. Yeah.
He had a lot of inventions. He had a lot of designs of
true.
airplanes and different things.
Well, this is it. I think there's a quote from Tesla. It's in a film, but he probably said it in real life. You know, it's like the world will forgive you for inventing one thing or something, but if you invent many things, you know, it doesn't want to know. I've forgotten the exact quote.
Maybe it's too confusing.
Yeah, it's just like, oh, you know, you're meant to be good at this. You're good at X. Don't bring Y and Z into it.
Then you are mixing it up and confusing.
Yeah, I guess. Or you're just showing off. That's probably the thing. Certainly in Ireland, I think, like, if someone started doing everything amazingly, everyone would just get annoyed with them and be like, oh, you're just showing off. That's a very Irish way of looking at things, I think.
Another functor aspect of our humans. We repel. Repulsion.
That's it. So, okay, I was looking for this. This is very relativity here, isn't it? For sure.
Oh, yeah. This is about, what is that, lattice?
No, that's just special relativity, isn't it? The light bouncing as the rocket goes.
Oh, yeah.
This is basic stuff, you know. I mean, look at the
bending of light. Okay.
The maths and all. But
see, everything is based on Pythagorean theorem, you know.
Yeah.
If you look at it,
it's
even
so
Riemann is based on Pythagorean theorem.
Really? But
yeah, if you look at deeper.
Yeah, but it's based in complex space, so it's everything is.
Yeah, only thing it applies to complex space, but the fundamental principle behind it is Pythagorean.
All right, that's fascinating. Yeah, I suppose it's true. But, yeah, I haven't, but the rules are slightly different, are they? Well, they're slightly different.
Yeah, but he extends it. When he extend it, it becomes more complicated with tensor and all those things. You know.
Yeah, it's crazy. It's very.
I work very similar, right? I also start with Helmholtz, very simple. But when you actually put into the theory, it is with gauging and all, it's quite complex, you know, what we come up with the theory.
There's Mitchell some more experiments, and so on and so forth. Now, it must have been either it's not here, or I imagined it, or
which one is that?
It's just a very simple. I think it's this kind of thing, you know, where you have like.
Oh, that he shows the Emery. We have this explanation in our falsification theory.
Yeah. No.
Why it was like comparing apples and oranges.
Oh, okay. No. I thought it was something else. It's just a very simple thing. I think it might be way at the start actually of this book, and it's just talking about how you can, you know, the way you have these land surveyors who are like at roads, and they have laser and they're measuring distances, and they're measuring angles, and Minkowski started doing that with space-time, and they were saying, oh yeah, I just found there's something about it very dubious, you know, but I suppose they developed the theory and it went on, and obviously, you know, when you're talking about rotations in like Lorentz transformations and rotations, which are equivalent to a contraction of the object. So like if I have, I don't know if you can see this, but I have this, and then if I rotate it, from your perspective, it's getting like smaller, the cross section, yeah? So that's like a contraction in space, because
it depends on the angle of perception.
Sorry, what?
Depends on the angle of perception.
Yeah, but if you're like here you're in 3-dimensional space, and then this is moving into the 4th, and your angle of perception of the 4th dimension is the same, no matter which way you're looking at it, right? Well, kind of.
Yeah, that invariability, invariance.
Right.
Invariance of.
I think this is probably an analogy, but that's how they do it. Like, so if this is the object in space-time, if this is space, it's traveling along, this is time, and then it begins to move more in time than it does in space, and then from the space point of view, it's contracted. Its cross section is smaller. So it makes perfect. So, but that's that's then projected back onto the space, to say, look, it's gotten smaller. But it's purely mathematical. Like this rotation here isn't visible. It's it's just a cool way of doing it. I'm sure there's other ways of doing it, right? Oh, you froze again.
Yeah, I couldn't hear you. Yeah.
Yeah, and what I was saying.
You both froze. Yeah.
It's just a cool, like, so basically this plane down here is reality. This is space, and as it's moving in time faster, its cross section is smaller when it's projected back down onto space, this is the only plane we see it. So we just see the projection. But this is purely, what I'm describing here with the rotation is a purely mathematical thing. I mean, it's a very good and cool way of doing it, but I don't think it's just one way of doing it. There's probably other ways,